everyone, in this video we're going to be talking about composite functions. So we're going to form a composite function and then also find the domain. Okay, so let's get right into it. So the definition of a composite function is the following. So if you're given two functions, we'll just name them f and g. Then the composite function, meaning a function that you compose out of the two functions, is denoted f of g, or f composed with g. So notice how we read this. This symbol is a composition symbol. It's not a O or a circle. It's really a symbol, a math symbol. It's related to plus, minus, multiply, and divide. It's an operation. So it's a new symbol for you. It's an operation meaning composition. So f composed of g, or f composed with g. And a lot of times you'll just hear people say f of g. So that's the way I read it. I say f of g. Okay, but it's composed. Just like music, you compose music with musical notes. So you have a composition of a function that you compose with two functions. So it's defined as the following. F of g of x, notice how I read that out loud. F of g of x is the same thing over here on the right side of the equal sign. Look what we're doing. We're putting the function g inside of the function f. So normally you see things like f of x, but instead of putting an x here, we're actually putting another function in that spot. So where we would normally place an x and then a number would take that spot, we're putting a whole function into that position. So f composed of g of x. Then the domain of a composition function is the set of all numbers that we're going to call x in the domain of the inside function. So notice this is the one that's getting plugged into the other function. So the domain of the inside function, for which the result, notice g of x is a y value. So g of x is like y. So this is the output. So for which the output is in the domain of the outside function. Okay, so let me restate this and we'll do examples so it'll make sense. Okay, so we have an inside function, g of x, and the domain for the composition function is all the numbers that you can plug into the inside function, as long as that output that you get, so as long as the output from that inside function is going to give you a real number when you plug it in to the f of x, the outside function. Alright, so let's make this make sense with some examples, but let's talk about the composition function and just sort of give you a diagram for it. Hopefully this helps a little bit with the idea. So what this diagram is saying is kind of giving a visual for the domain of a composition function. And so basically we're saying that we have an original function g. So this is for this example here. This is for plugging in the function g into the function f. So there are going to be possibly some numbers that you can plug into g, which is, this is the domain of g, this whole thing. This is some set of numbers that you can plug into g. There's going to possibly be some numbers that when you plug them into g, you're going to get an output, a y value, which is this part here, that don't necessarily work when you plug them into the function f, which is what you're trying to finally plug into. And so this just says like, okay, there's some numbers in your function g that you can't actually end up plugging into the function f at the end, but other numbers work. So like whatever numbers these are, you plug those into g, and then those results get plugged into f, and then you get a final answer. And we'll work through some examples so you can kind of see that, what this is saying, but it's essentially saying that the numbers that you're plugging into finally, to the final composition for f of g of x, it doesn't always coincide with the domain of g. Like everything that originally worked in the function of g doesn't work always at the end. Here, let me give you a quick example. So let's say that you had g of x was just like x plus 1, okay? And then let's say f of x was just 1 over x. If you plug in this function into this one, it's going to go right here in this spot. It's going to take the place of the denominator. And so then we're going to get 1 over x plus 1. So originally, for this function back here, g, we can plug in any number we want. All real numbers plus 1 are going to equal a real number. So that domain was all real numbers. But when we did this composition, look at this one. This result, f of g of x, there's a problem with the number -1. If x is -1, then this is undefined. This is going to be dividing by 0. So even though all real numbers worked in the original function, I have to cross some of those numbers off. In this example, it would be the number -1. I'll just kind of put that here. -1 would be the problem because I can't plug that into the final result. Okay, so we'll go again through some examples. So let's start by evaluating a composite function. So suppose that we have two separate functions. F of x is 5x minus 1, g of x is 3x squared, and we're going to do all 4 of these parts. And so notice we're plugging in numbers each time. And so we can rearrange this, and this is what I recommend every time. This says f composed of g of 1, so I would write it like this. F with g of 1 plugged into it. If that's my first step, then I can tell more quickly what I need to do to move forward. Okay, so that would be my first step every time. It helps me figure out what's my next step to do. All right, so g of 1, that means what is the output? So we'll just write it down for this first one. What is the output from the function g? So from g, if x is 1. So that is the translation for g of 1. So in math, it's a lot of writing to write this sentence out. So we use these symbols. G of 1 means the same as this sentence. Okay, so if you plug 1 into here, you're going to get 1 squared times 3. So that's 3. Okay, so g of 1 equals 3. So then this composition is really saying f of 3. And so you go to your function f, you plug a 3 into that right here, and then you get the final answer, 14. Okay, so that's our first composition. We composed f of g, and we found that value when we plugged in 1. Plugged in 1 into the original, got out 3, and then 3 got plugged into the outside function, and then we got our final answer of 14. Okay, so sort of to sum up what we did with the blobby stuff on the previous slide, we chose 1 to plug into our function g. Okay, so g took us from plugging in a 1 to here. The output of g was 3 when we plugged in 1. And then our function f, we plugged 3 into that, and the output was 14. Final answer. Okay, let's do the next one. So g of f of 1 means g composed of f of 1. So this is the y value when you plug 1 into the function f. So y when x is 1. Plugging it into f this time. Okay, so we're going to get 4. That's because the function f, if we plug a 1 in right here, that's 5 times 1 minus 1. So that's 4. So f of 1 equals 4. And now we want g of 4. So then in the g function, you're going to put a 4 into that. And then that's going to be 4 squared, which is 16, times 3. Final answer, 48. Okay, so we plugged in 1. This time got plugged into f first. And then that gave us a 4, and then 4 got plugged into g, and that gave us 48. All right, next one, f of -2. This time, this is saying plug a number into f, find out what it equals, and then plug it in that answer into f. Okay, so this is the y value when x is -2 in our function f. Okay, so that's going to be -11, because if we put a -2 into our function f, it's 5 times what used to be x 5 times negative 2 minus 1 is negative 11. So now this says f of negative 11, and we're just plugging back into that same function. So it's okay that we see f of f, it's just saying that we're composing a function with itself. So f was 5x minus 1, and so we just happened to use the same function twice this time. So the first time we plugged in negative 2, we got out negative 11, and then the second time we plugged negative 11 back into that function, and we got out negative 56. And so that one is just f getting plugged into itself. So for the image for that, negative 2 got plugged into function f, the output was negative 11, and then that output got plugged into the function f again and gave us negative 56 as a final answer. Okay, how about this one? G of negative 2. Rewrite it as g composed of g of negative 2. So plugging negative 2 into the function for g, where there used to be an x, we're going to get 12. So this is the y value. So when x is negative 2, y is 12. And we're plugging that back into the function g because we were told to compose g with itself. Okay? So then back into the function g, which g of x was 3x squared, we're just plugging 12 into that. So 12 squared times 3, 432. Okay, so just a quick reminder again on how that one worked. You start by plugging in negative 2 into the function. The y value when you did that was 12. And then you plug in 12 back into that same function to get your final answer. So we plugged in negative 2 into the function g, got out 12, and then plugged 12 back into g again, and got out 432. Okay, so now let's work on finding the domain. So suppose that this is our f function, and this is g. Let's find f of g, f composed of g, in part A, and g of f, g composed of f, and then find the domain of both functions. Okay, so the domain of f and the domain of g are all real numbers, so you want to look at what's the starting domains for both of them. Notice for this function up here, no matter what number you plug in for x, you're going to get a real number out. So that's why the domain for f, so we'll say domain for f is just all real numbers, negative infinity to infinity. Same thing with g. If you plug in any number for x, you're going to get a real number out. You're not going to get something undefined or imaginary. So that's why that domain is also all real numbers. Okay, so now this says f composed of g of x, and so I would write it like this: f with g of x inside of it. So f composed with g of x. All right. The difference now, as opposed to the previous example, is we don't have numbers to plug in. We're just plugging in the entire function and then simplifying. So there's no number to plug in for x. We're just saying, hey, exactly where there used to be an x, I'm plugging in g of x. Okay, so let's kind of walk through what happened here. Let me write down the original's right here actually. So g of x is going to get replaced by what it equals. So let's take one step at a time. G of x is in the parentheses, and we know that it equals 3x plus 1. Okay, that's because that was given. Okay, so that part's done. Now, f of 3x plus 1 means you're plugging 3x plus 1 into the function. So let me try to make this part make a little bit of sense. If I said f of, let's go with 0, then hopefully you would know that that means everywhere there was an x in this function, I'm going to put a 0. So I'd say 0 squared plus 2 times 0 minus 5. Okay? If I said f of, let me just make this up, f of heart, then everywhere there was an x, I'm going to plug in a heart. So heart squared plus 2 times heart minus 5. And so what we're doing when it says f of 3x plus 1 is everywhere there was an x, I'm putting a 3x plus 1. So 3x plus 1 squared plus 2 times 3x plus 1 minus 5. So it doesn't matter that what we're plugging in has an x in it. I think that might be why some people might think this is confusing. It's okay. It's okay that there's an x inside what we're plugging in. Just think of it as exactly like I did here. Just like we plug in numbers or any symbol, it's the same thing. It just takes the place of each x. Whatever's in this parenthesis just takes the place of the x's right here. And so that's why this used to be x squared plus 2x minus 5. And so the 3x plus 1 just took those spots, just took the places of those x's. So if you have that step, that's one of the hardest steps. So if you have that one, then you're good to go. The rest is just simplifying. So after that step, just simplify. Okay? So we have 3x plus 1 squared, so you're going to FOIL that out. So that's this part here after you expand that by FOILing that out. And then over here you're going to distribute the 2. So that's these terms. And then minus 5. Then combine like terms, all your numbers here. And you get 9x squared plus 12x minus 2. That is f composed of g of x. Now to talk about the domain. So the domain of both functions originally was all real numbers. And if you notice this domain, this resulting function, there's no restrictions here. So because there was no restrictions on the two input functions that we kind of composed together, no restriction on the inside one, g, and then no restriction on the outside one, f, then the domain, and no restriction on this result, this domain is all real numbers as well. So the domain of f of g of x, our composition, is just also all real numbers. Okay. One more thing to mention on this before we move forward, just to bring this together with the previous examples with numbers. Let's say we were asked to find something like this. Let's say it was f composed of g of some number, let's just say 1. Well, we can do it the way we did it on the previous example, or if you want to verify, you can actually plug in 1 into the result here and you'll get the same thing. So you can do it the way we did it in the previous example if there's a number here, or you can do it the way we did this example, part A here, and then put the number at the end into the final answer here, and you're going to get the same result. Okay, so let's do this other one. This time g composed of f of x. So that means g is outside and f of x is getting plugged into it. Okay, so first just replace f of x with exactly what it equals. So f of x is in the parentheses, and we know that f of x is x squared plus 2x minus 5. Then think about what this says. This says g of something. So g of something, doesn't matter what the something is, it's going to get plugged into the function exactly where there used to be an x. And so for us, that whole big thing here, this trinomial, is going to go in the place of x. So just like before, if I had something like g of smiley face, I'm going to put the smiley face where there used to be an x into my function. And so on this one, we're saying g of x squared plus 2x minus 5. So it's taking the place of the x in the parentheses there. Okay, so that's exactly what happened here. This used to just be x right here in the function. We used to just say x. We erased the x and we put this whole thing that was in the parentheses. Then, again, like last time, that was the hardest step. The rest is simplifying. So after this, you just simplify. Alright, so let's go ahead and work this one out. So we have to expand or FOIL this part in the middle out, this trinomial. So I want to show you the box method on this one because it's really easy to use this when we have like a trinomial like this one. So it helps stay organized. So I put one factor on top, another factor on the side, and then I just multiply every row and column. Okay, so let's form our box real quick, and then we'll fill in the center. Okay, so we have x squared times itself, which is x to the fourth, and then x squared times 2x, so that's going to be 2x cubed. Then negative 5 times x squared, so that row's done. Then 2x times x squared, so that's 2x cubed. 2x times 2x, so that's 4x squared. And then 2x times negative 5, so negative 10, let's fix that. Negative 10x. And then we'll do our last row. Okay, x squared times negative 5, 2x times negative 5, and negative 5 times itself. And then you just combine all of these terms. And the nice thing with this box is most of the time the diagonals are like terms. So here's what we have. We have 3 times x to the fourth, and then this is a total of 4x cubed. And then over here, if you add up the x squareds, you're gonna get negative 6x squared. And then this is negative 20x, and then plus 25. Okay. And then we'll distribute the 3 and add 1. So this is going to be 3x to the fourth plus 12x cubed minus 18x squared minus 60x plus 76, because I'm going to add that 1. So 75 plus 1. And there's no like terms, so that is our final answer. That is G composed of F. So G with F plugged into it. And then the domain of this result is all real numbers, because the domain of the original two functions was also all real numbers, and there's no restriction on this final result either. So any number can get plugged into this one, so the domain is negative infinity to infinity. Okay, so now let's find the domain of something a little bit more interesting. Those last two, not too interesting as far as the domain goes. So this time, F composed of G, and find that domain. Okay, so take a look at F. It's 1 over x plus 4. G is 4 over x minus 3. And so, this is a first note that the domain of G, the one that's getting plugged in, so notice G is the inside function. That domain is all real numbers except 3. We cannot plug in 3 in this function because it would be undefined. It would be dividing by 0. So no matter what happens when we do our composition, we have to exclude 3 from the domain. Even though it's possible that when we do our composition, it would look like 3 was okay to plug in, but because it doesn't work in the original inside function, because 3 doesn't work here, we have to exclude it from our domain for our composition. Okay, so next notice that the domain of our outside function is any real number except negative 4, because if you put a negative 4 here, this is going to be undefined. And so because we are plugging g of x into our function f, this is the y value. Okay, so this is the y value of g getting plugged into our function f. We have to figure out, well, is that y value, g of x, is that ever going to be negative 4? Because if it is, we can't actually plug that into our function. It would cause a problem. And so what you do is you look for this. You say, is g of x ever negative 4? Because if it happens, we have to find the x's that make that true and get rid of them. Alright, so what this says is g of x, is it ever equal to negative 4? So you're just solving this equation for x. Alright, so anytime that you're solving for x and it's in a denominator, the first thing you actually want to do, or one of the first things you want to do, is go ahead and get it out of the denominator by multiplying by that denominator. Okay, so multiply both sides by the denominator. It's going to divide out on the left for us, and then we'll just distribute on the right. Okay, so we have 4 equals 4x plus 12. Let's go ahead and subtract 12 from both sides. So we're going to get negative 8 equals negative 4x, and then divide, and we'll get x is 2. Okay, so we now know that if we plug in 2 into g, so if we plug 2 into g, we're going to get out negative 4, and then we cannot plug in negative 4 into our function f because it's going to be undefined, and so we can't, that means going all the way backwards, we can't plug in 2 into our original function or our composition function. So the domain for our composition is all real numbers except 3 from the original function g, and now also 2 because it would cause a problem in our composition function. So we had to look at both the original domain of our inside function and the resulting function, what happens for that one. Okay, so let's do this one. So this time we'll actually find the composition and then the domain that way. The last one we didn't actually do the composition, but this time we will. So find f of g first and the domain. Okay, so first notice that f, you cannot plug in negative 3, so we're going to exclude that. And g, you cannot plug in 2, so we're going to exclude that. So we'll just keep those in mind. Now, f composed of g is f with g plugged into it. And so that means exactly where there is this inside of the parentheses, I'm going to put 3x minus 2 because that's g. So then the very next step, this means where there used to be an x in my function, I'm plugging in whatever's in the parentheses. So it used to be x, but now it's this whole quantity. It's the function g. It's taking this place of x. So notice I have 1 on top, fraction bar on bottom, and then what used to be x plus 3. So that's this right here took the place of x. Right here took this place right there. And now the rest is to simplify. Okay, so that was the hardest part, knowing that I'm plugging in right in this spot right here. Okay, so we're going to simplify, and on this one of the first things we can do is just multiply. We're going to say the top and bottom of this giant fraction here by x minus 2. Okay, so if I multiply top and bottom by x minus 2, this is going to distribute here. That's this part. It is going to multiply here, but it's going to divide out with that one, and then it's going to multiply by 1 here. Okay, sorry for the scribbles, but the factor divided out on the first term, but it got distributed to the 3 on the next term. Okay, and so we multiplied on top and bottom, because anytime you multiply by something over itself, it's really multiplying by the number 1, anything over itself. Okay, so if you simplify that, just distribute, that's going to be 3x and minus 6. So we have 3x minus 3 on bottom, x minus 2 on top. Okay, and if you want to, you can factor that as 3 times x minus 1. Okay, so from our function that we composed with g in the inside, originally g we couldn't plug in 2, so we still keep that. And then our resulting function, it was, so f composed of g was x minus 2 over 3 times x minus 1. And so notice now 1 would be a problem. If you plug in 1 into this function, then you're going to get the bottom to be undefined, the whole thing to be undefined, because the bottom would be 0. So now we can't plug in 1 into the resulting function. And so our final answer for the domain is that x can be any real number, except it can't be 1 or 2. And so what I want you to notice is in this final answer for the composition, it doesn't look like 2 is a problem. If you plug in 2 into this function, it's going to be 2 minus 2 on top, 3 times 2 minus 1 on bottom, which is 0 over 3 times 1, which is just going to be 0. It looks like 2 is okay, but because you couldn't plug in 2 originally into the inside function, then you have to still keep that restriction. You have to still include that original restriction and any new restrictions, which we had 1 as a problem now. So that's the whole point of finding the domain of f of g like this, looking at the inside function first, and then looking at what happens to the outside function. So you have to keep both restrictions. Okay, how about f composed of f? So f was 1 over x plus 3, so we're plugging that in to the same function. Okay, so just a reminder of how that works. This is what f looked like. This was the function f. And so whatever is in the place of x is going to just get erased. So this right here is going to get erased. And then you plug in what is in the parentheses. So this whole thing goes right here in this spot, which is exactly this part. Okay, and then we just start simplifying. So just multiply top and bottom by x plus 3 times x plus 3. And let me distribute that. So on top, on bottom, it's going to go here and here. It's going to divide out on the first factor, and then it's going to be times 3 on the second one. That's this part. And then on top, it's just 1 times x plus 3. And then that becomes x plus 3 over 3x plus 10. Okay? And so originally, we could not plug in -3 into this function f. -3 would be a problem. So x couldn't be -3 originally. And so we can do this one 2 ways. We're going to do it the way we did the previous example. But you can also just look at your result here. So I'm going to keep this in mind, but I'll show you both ways. Okay, so we want to know, when is f of x ever equal to -3? Because that would cause a problem. And so if we solve that and multiply both sides by the denominator, we find out that x is -10/3 would cause a problem. Okay, so we're going to exclude those from our domain. But what I wanted to show you was you could also, we'll separate this. You could also just look at the composition, because we already did it. If you hadn't already done the composition, then this method we just did, this would be easier. But because we already did the composition, we knew that the denominator was 3x plus 10. And so we know that we don't want this to be 0. So if we solve this and set it equal to 0, and we say 3x equals -10, divide by 3, oops, it's an ugly 3, then x equal -10/3. So it's the same answer, just 2 different ways to do it. Because we had already found this composition, we might as well have just done it this way. But if we didn't already find the composition, then doing it this way works just as fine. Okay, so the domain is all real numbers, except originally x couldn't be -3, and then also it can't be -10/3 because after we plug into our function again, that would cause a problem. Okay, so this is just a note on saying what I just did about the second option for you. Since we had already found the composition, you can just say that you don't want the denominator to be 0 and solve that way. Alright, let's try this one. So now we're going to show that 2 composite functions are actually equal. And so if f of x equal to 2x minus 5 and g of x, which is x plus 5 over 2, we can show that f composed of g of x is the same as g composed of f of x, and saying that they're both equal to the value of x. Okay, so this time we're showing this. We're showing that this is true, that this and this both equal x. And just giving you a heads up on what's coming, why we're doing this. This one is because this is going to come up in the next section on helping us with what are called inverse functions. So in the future, a function, so we'll have a function and its inverse, so we'll say like g and g inverse. When you do the composition like this and you get x both times, they're inverses of each other, but that's going to come up in the next section. Okay, so for every x in the domain, we want to find f of g of x first and then g of x next. Okay, so g of x, plug that into our function f, exactly where there used to be an x, so right here in this spot. So 2 times something minus 5, the something being g, this whole thing here, g. Okay, so 2 times the something minus 5. And then we'll simplify. Okay, so just divide out the 2. X plus 5 minus 5 is just x. So far we did half of it. F of g of x was just x. Okay, so let's go the other way. G of f of x. So this time we're plugging in f of x into our function g. So remember, g was x plus 5 over 2. So we are plugging in right here. So what's in the parentheses is going right in the spot of x, what used to be x. So 2x minus 5 goes right there. So plus 5 over 2 is added to that. Okay, so the 5's go to 0. 2 divided by 2 is 1, so that's x. So we did it. So we concluded that f composed of g of x is the same as g composed of f of x, and they're both equal to x. Alright, so again, one more time, the whole reason for showing this is to get you ready for what's coming up in the future, that you can verify that two functions are inverses of each other when this composition is true. So just note that in this particular example, we had 2x minus 5 is the inverse or opposite of x plus 5 over 2, and that's proven by what we just did right here. Okay, we're almost done. Just a couple of last examples. This time we're going to be finding the components of a composite function, so kind of working backwards from what we've been doing, so undoing it. So find the functions f and g such that when you compose them, f composed of g, you get this result, which is h. Okay, so we're starting with the composition here, and we're trying to undo it. Okay, so notice that the function here that we have given, it raises some expression, 3x squared minus 5 to the 21st power. And so you want to just do the most simplest way to decompose this. And so you can just say, well, it's the 3x squared minus 5 is part of it, and then the 21 power, the exponent of 21 is the other part. And so we can say that f is x to the 21st power, and g is just the inside part, the 3x squared minus 5. And so then if you put them back together, f composed of g is the result that we got. So then we know, based on this decomposition, that we could say the outside function, f, so the outside function is the 21st power, so x to the 21st, and then the inside function is that inside expression, so the inside part is just the expression 3x squared minus 5. Okay, so let's do that one more time. So find functions f and g such that when you compose them with g inside of f, you get this result. So this one's not as clear as the last one. We don't clearly see an inside and an outside. The last time the inside was in the parentheses, the outside was the 21st power. So this time we had to just do a little bit of thinking about how we can undo this. And so all you can really think about is saying, well, maybe this expression on the bottom can be its own thing, its own function. So if I just call that denominator my function g, then I can plug that into 1 over x to get the result that we have here. And so f of x is going to be 1 over x, and then g of x is just going to be the x plus 3. Because when I put them back together, and I plug in x plus 3 into 1 over x, then I get exactly what we started with. Okay, so just thinking about going forward after we undid this, we know that we're claiming g of x is x plus 3. We are saying that f is 1 over x, so this x plus 3 is going right here in the place of the x, which is exactly what we started with. So these last two examples are just sort of undoing what we did, so working backwards, finding the components of the composition function. Alright, well, we did it. That is it for this one on composite functions. And so thank you for watching.